is capturing the screen here. Try not to like step in front of it.
You're not blocking the screen.
Yeah. Just give me a second here to get my stuff set up and we can get started. There we go. All right. Hello, my name's Ian. I'm a full stack developer. I do mostly Ruby on Rails, but a lot of JavaScript because that's the life that full stack development entails. Lately Angular, but yeah, I'm an equal opportunity JavaScripter, I'd say. So what I am going to talk to you today about is asynchronous JavaScript. So asynchronous APIs allow work to happen in the background while the execution of the current thread continues. So you call a function, let me get my notes straight here. You call a function, and instead of that call blocking and only returning once the result is ready, like is kind of the standard model for programming, in asynchronous operations, the call returns right away and says, okay, I'll have an answer for you later on this. And how do we receive that answer when it's ready? Well, we provide a callback function. It's just a function that gets invoked once the operation is completed. That function can take arguments that will hold the results of the operation, if any. So, as JavaScripters, you've all seen asynchronous operations by now. We use it on the front end, most often in like AJAX network requests, but also in a number of other operations, interactivity, and I think some of the newer web APIs are asynchronous, things like that. And for those of you who use Node, you're very, very used to asynchronous JavaScript. Node uses async operations as kind of a core performance principle. So everything in Node, everything that involves any I/O, so that's reading from a disk, doing network stuff, anything that doesn't just happen in processor and RAM, has an asynchronous function to do it. So asynchronous APIs have some really great performance characteristics because they sidestep the most common bottleneck, which is I/O operations, and having your whole program block on an I/O operation that is relatively slow. And sometimes asynchronous is really the only model that even conceptually makes sense, such as when you're dealing with interactivity. You can't have any other model except responding to events. But asynchronous code can be more difficult to reason about than standard imperative code. Standard imperative code is pretty straightforward because you do something and that thing happens and it's done and then you move to the next line. And so it's very easy to keep track of what's happening and to kind of reason about your program. I'm going to go grab some water real quick. Okay, so when you talk about asynchronous code, the first objection that people always come up with is the pyramid of doom, or sometimes also known as callback hell. This is what the pyramid of doom looks like, essentially. You basically get a whole bunch of deeply nested callbacks. So like in this example, where first we make a call to the database to pull a record out of a table, and then we use that record to look at the file system, see if a given file exists. If that file exists, then we read that file. Then we want to process the data that we got out of the file. Then we want to write it back to the file. And then if that has succeeded, we want to remove the record from the database. And then if that's succeeded, we want to send a response. This is like a web server, so we want to send a successful response saying that the operation succeeded. So this is like an example in a hypothetical node scenario in which you're kind of doing this operation. And so you end up like 8 levels of indentation deep, and by the time you're in the middle of it, you've completely lost track of what's happening in what order, and it's just terrible. So this is kind of what people always, like the first thing that they think of when they think of asynchronous boogeyman. Now, it's true that this code sucks, but I don't think it makes sense to blame the asynchronous piece for it. So let's pretend that we've got a magical synchronous API that does all of these same things, but will let us flatten this code out, so it's no longer using callbacks. Okay, so this does the same stuff, doesn't use callbacks, it's now just, you know, the calls return their values. This may not look as bad visually, but I contend that this code still sucks. It's doing way, way too many things in this one big imperative block. You should have code that does, like, you should have small functions that do one thing well, and this code does a whole bunch of different things, and it just mashes them all together. It's really hard to separate the concerns. You have to read through all of it to know what's happening. So the problem isn't that the asynchronous style made our code bad, it's that our code was bad, and asynchronous style just made that very, very obvious. So in fact, if we clean up that asynchronous code that I showed you and factor it into a bunch of small functions that do one thing well, which is a good programming practice no matter what style you're writing, you'll see that the pyramid of doom essentially goes away. So let's just walk through that real quick. So here, my first function is process and write to file. So this is just going to accept some data, run our processing function on it, and then write it to a file. Now you'll see this function accepts a callback as its second argument, and when it's done, it will call that callback to say that's done, and it will pass it any information that needs to. In this case, that's just going to be a success or failure, essentially. So now here's our second function, read and process file, which is going to check if the file exists. If it exists and it is a file, then it'll read it, and then it will call its callback. And this is just going to take a file name as its first argument to look for. Okay, moving on, we've got a function to pop a record out of the database and do something with it. Now you'll see that here we've genericized this so that it's no longer doing something specific with what is popping out of the database. It just accepts another function to call on the record that is popped out. And then, so now we've got that small generic function. Now we'll wrap in another one, pop and process file, which is going to use the actual table name that we want for unprocessed files in our database. And then, so it will, so pop and process file will call db pop and handle. db pop and handle will take care of actually getting the record out of the database. It will call the processing function, which is read and process file, or it's this callback, which read and processes the file and then processes and writes to the file. And then that will call the callback to say that that part has finished, which now sends it back up to db pop and handle, which says, okay, it's successful, delete the record. And then it passes it back up to its callback to say that it's finished. So now that we've done all that, our final little bit of code that actually runs is going to call that management function and just get a success or failure. If it's successful, then it'll write a success message to our web server and finish. So this code still has all of that same async stuff going on, but it's not nearly so bad. Each function in itself was easy to understand, and we've genericized some of the functions so that we could conceivably use them in other parts of this imaginary application that we're writing. So I don't want you to worry about the pyramid of doom. I don't think the pyramid of doom is really the problem. The way that you avoid callback hell is you write decent code, and if you don't write decent code the first time, you refactor it as soon as possible, and you commit to doing that. It's the same good coding practices that you should be following anywhere. The same ones that help you out in synchronous programming will take you a long ways with asynchronous. Which is not to say that there's nothing to worry about once you start using a serious amount of asynchronous APIs. This is what I think you should be worried about. I'll come back to this in a little more detail later, but what you get is you get these complex sets of dependencies where you've got several things happening at once, and some things have to wait on other things to finish, some things happen in parallel. And then on top of it all, you have to handle errors in some sensible fashion, whatever that means for your particular application. So it's this sort of logic that you can quickly become difficult to deal with, especially when you're encountering it, all the time in the course of writing your application. So there's various solutions that exist that take different approaches to helping you tame this sort of asynchronous code. I want to give you a better framework for evaluating these solutions than just Pyramid of Doom. And I want to help you worry about the right things and not worry about the wrong things. So I've devised a set of 3 crucibles, which are little theoretical problems that I think are relevant to the most common use cases that you'll encounter as you build applications with asynchronous APIs. I know you say crucible and everyone either thinks chemistry or witches, but one of the meanings of the word is a test or a trial, a test of faith, sort of. So I'm going to walk you through these crucibles, and we'll use them to evaluate 4 popular solutions for taming asynchronous code, so you can see how each one works, and you can compare them to each other and see where one might have strengths or weaknesses. And then when you go out and find another solution that I didn't cover, or you have a project and you need to pick a solution and you're trying to decide which one you're going to use, I want you to remember these crucibles. I want you to use them to evaluate the solution, or the solutions that you're considering. I want you to pick a solution based on how well it solves these sorts of problems, not based on how many indentations or curly braces it does or doesn't have. So let's meet the 3 crucibles. The first one, very simple. Just you do a single asynchronous operation, you get a result, and you pass that result along to some output. And drew beautiful ASCII diagrams to illustrate all of these. So this crucible, you'll be doing this thousands of times as you write asynchronous code. This happens all the time. So this crucible just exists to kind of kick the tires and see how each of our async solutions handles this sort of the basic unit of asynchronicity. The second crucible is another, I think probably the next most common situation that you'll run into. This is that you have multiple asynchronous operations and you want to run them all in parallel, because that's the whole point of having this be asynchronous, is that you can run them all in parallel. So in this case, we're just going to say you have 5 database accesses. You want to hit the database 5 times. You want to do it all in parallel so that you're not waiting for the combined time that it takes. You're just waiting for the longest access. So here's the problem with this one, is that you need to wait until they're all finished before you can do whatever you're doing with the output. You need them all to be present to move on to your output step. And if they all complete really fast, then you want to finish as fast as possible and move on to the next step right away. But if maybe one of these operations is like a cache miss, and so it's got to go read the disk, and so that's going to take comparatively much, much longer than all of the others. But you don't know which one of these 5 operations is going to take the longest, and you can't really set an effective upper or lower bound on any of them. So the problem for this crucible is, how do you finish as soon as possible, but no sooner? And now the third crucible, which is the one I showed you earlier. This one is really evil. I designed this to kind of represent the most convoluted logic that you're likely to run into when you build something based on asynchronous APIs. So what we have here, starting up at the top left, I should really get rid of that. I didn't realize it was showing you my menu bars and stuff. There we go. That's better. Okay, starting at the top left, so we've got, again, a couple of database accesses. We want to run those in parallel. Then we've got a collate step for which we need the results from all of the database accesses. Meanwhile, we've got a network access down on the bottom. We want this to be running in parallel with everything, because it could be really slow. But we then need both the result of the collate and the result of the network access to move on to our output step, to go forward with that. So this is the sort of stuff that will come up once you really start to get deep into an app that uses asynchronous stuff. And if your given solution can handle this case without breaking a sweat, then I think it's pretty well equipped to deal with the sorts of problems that you'll see. So I built a little test harness to sort of run the code against these. It just kind of does some setup stuff, and then it emulates these I/O operations so that we can have a realistic sort of little playground to write our code in. So I want to just walk you through the API of that real quick before we get started so that you kind of know what's going on. So these are the methods that I provide in the test harness. First one is the just an input function. You just give it the number of the crucible that you're running, and it's going to give you some IDs or whatever input you need to run it, and I'll show you how we are using that. These are our finishing functions. So once you've successfully finished with the given crucible, you're going to call output and just give it the data that the results you've accumulated. And in this case, I just set it up to console log to the screen so that you could, kind of see that your results were there. Now, I also set it up so that if you pass it, if you run it with a certain parameter, the database accesses will start throwing errors. So that we have to actually handle errors realistically. So if you get an error at any step in the process, in our case, you just call this errored function at the end, and that's just to kind of acknowledge that yes, an error happened, and in real life we would log it or recover or do whatever it was that we were going to do. And then now the test harness also provides these methods that emulate the operations that we're going to be performing. So this one is the database access. You pass an ID and then a callback. The callback is kind of the indicator that this is asynchronous, right? So the callback is going to return to you an error and a data value. The error will be null if everything went fine, or it will have an error in it if an error was encountered. The data value will just be an object, a very simple object in our case. Behind the scenes, these are just using timeouts, essentially, to kind of fake the act of waiting for a database or a network or whatever to respond to you. This is our collate step. It takes two objects as input, and then the callback, again, returns either an error or a string result. And this is the network step. Again, takes an ID as input, has a callback that returns either an error or an object as a result. Okay. So these are the four contenders that I want to run through these crucibles today for you. First one is just regular old JavaScript, just implementing ourselves, not using anything to help us out. And part of the reason I'm showing this one to you is that this gets tossed around a lot in discussions where people are like, oh, you don't need any solution, you can just do it yourself, it's not that hard. I'm hoping that including it in this panel will give you a chance to see how it performs pretty poorly, and hopefully I can dissuade you from taking this route. Second is ASYNC.JS, which is a library that you can pull in and use essentially. Third one is Promises, which you may have heard of. Perhaps through jQuery was your first introduction to it. And the fourth one is ICEDCOFFEESCRIPT, which I will talk about when we get there. There's a feature in the upcoming ES6 standard for a thing called generators. And one of the things that those allow you to do is to make asynchronous code basically look like it's synchronous. And I know there's at least one popular library based on this called task.js. I'm not going to cover these because, for one, I don't have personal experience using them, so I wouldn't really have that much to offer you. And for two, ES6 isn't out yet, and even once it is, if you're working on the front end, you're never going to get to use it. It's going to be years before you can realistically use it, because this feature does not transpile back. There is no way to support this particular feature in ES5, at least that I'm aware of. So you really can't use it unless the browser natively supports it. So if you are supporting real users on real browsers, you can't use it for the long foreseeable future. But if you like it, if you're on Node and so you can use ES6, or if you just don't care about 40% of your users, if you want to consider this, I've given you the evaluation tools. They'll show you how to use them. So just write your own little test and see how it compares to the other options out there. Okay, so let's start out. Crucible 1 is a very simple one. So we'll begin with just a vanilla JavaScript implementation. So this first line is just pulling in that test harness that I told you about. The second line, we call the input function. We tell it, okay, we're on Crucible number 1, so give me the relevant data as the relevant input for this. So in this case, it's just going to give us a single ID, because that's all we need for this Crucible. Now we call the database access with passing it in that ID, and then a callback function. The callback function takes an error in the data, and from there it's pretty simple, right? When our callback function is invoked, we just check, we see if it's errored. If the error is present, then we call the errored function on our test harness just to say, yeah, it was an error. Otherwise, we call the output function with the data that we received from that call, just to say, yeah, we got it. Here it is. We're done. Okay, so now if I can, yeah. So I'll just demonstrate this running for you. So I have it logging kind of when each operation happens. The operations wait sort of a semi-random amount of time for each of them. And then down at the bottom, you can see where it's logging out the data that we received. So in this case, I just return a simple value as our, the result of our database query. Okay, moving on to ASYNC.JS. This is literally exactly async code. This is because ASYNC.JS is a library that's still very much based on callbacks. It stays very close to the standard callback model, so in this simple case, there's nothing that it can really do to improve on that or to help us. But it will definitely help later on. Promises. So for promises, we have to wrap that whole evaluation harness in another thing to make it actually return promise objects. And this is a big consideration when you're using promises, is that you need your interfaces to support promises. So just the standard callback-based setup that I showed you earlier isn't enough. We need something that actually returns a promise, which is a special object with certain specified behavior. So I had to make this whole separate file to kind of wrap and redefine the API. I'm not going to show you the whole thing, but this is kind of a representative example. So this is now our promise-based DB access function, in which we construct this deferred object, and then we either reject or we resolve it based on if the database access was a success. So if you don't, if the library you're using doesn't support promises, you might have to do something like this, which kind of sucks. Okay, so here's our Crucible using that. So now you'll see. Oh, so I should mention all of these examples will be requiring the Crucible library and doing the ID stuff, but I'm not going to show you that every time because it's boring. So it'll disappear after this. Just don't worry about it. It's still up there. It's just not on the screen. In this case, I'm giving it a different name. I'm naming it C_P just so that you remember that this is actually a different API than what the other examples are using. So we pull that in. We call DB access on it, and we pass it an ID. Now this is a different DB access, right? Because we're no longer passing it a callback as a second value. It's just the ID, and then that will actually return a promise object. On the promise, we define this then function, and that's what gets, or we define two functions really, and give them to then. That's what gets invoked when this is finished. So with this simple example, it makes it pretty obvious that promises are really just callbacks wrapped in a bunch of extra ceremony. The only real difference between this and what we've seen before is that there are now two functions, one for success and one for failure, instead of one that takes two params. So in this case, I think promises really aren't any help, but they will be more useful later. Okay, IceDCOFFEESCRIPT. This is a variant of CoffeeScript. CoffeeScript is a language that compiles to JavaScript, so IceDCOFFEESCRIPT is also a language that compiles to JavaScript. IceDCOFFEESCRIpt is the same as CoffeeScript, but it's got a little extra layer on top that helps with asynchronous stuff. If you don't know CoffeeScript, it's okay. It's not too relevant here. Just try to follow along. I think it won't trouble you too much. Okay, so here, once again, we pull in our library. We just have an ID hard-coded here instead of getting it. But what's noticeable here is that IceDCOFFEESCRIPT has actually taken our asynchronous operation and made it look synchronous. So we make this call to DB access, and then there's no callback. We just go to the next line, and we perform on the results. And how it does this is these two keywords of await and defer. So the await sort of declares that we are going to wait for an asynchronous operation to finish. And then the defer happens in place of the callback, essentially. So you see we have defer, error, and data. Those are the two values that we're expecting from this asynchronous operation when it completes. So you write this code, and then IceDCOFFEESCRIPT basically behind the scenes compiles it into JavaScript that works in the asynchronous fashion, even though it doesn't look like it on this screen. It's pretty cool. I'm not going to actually go into how it does it here. But if you're interested in it, you can go check it out, play around with it. You can compile this and see the output JavaScript and just read through it and see what it's doing. And it's a very neat trick, I think. So yeah, so we have this line. Yeah. Yeah, it's pretty much what you'd expect, especially in the simple case, because yeah, it's doing more or less what we did in our first example. It'll look a little different because they have some sort of special stuff built around it, and we'll see it do a little more in the next Crucibles. But yeah, it's basically doing that. It's just doing it with a syntax feature of the language, essentially, which is cool. It's very elegant. It's very impressive, I think. Okay, moving on to Crucible number 2. This is the mini operations in parallel one. So vanilla JavaScript. You'd think that this would work, right? So we set up a results array. We set up a little counter variable to count how many asynchronous operations are currently, pending. And then we loop through the array. We increment each time for each member of the IDs array. And then we call a DB access function on it. And we give it a callback, and it gets the callback, it shoves things back into the results array. You'd think that this would work, but JavaScript does this insane thing where the invariant variables of the for loop are basically by reference instead of by value. And so when you have an asynchronous thing in there, this I is actually getting updated in all of the callbacks. So by the time any of these callbacks are called, the I is going to be like 4 in all of them. So if you do this, you'll get this array with where all of the values have overwritten each other, and there's just one result in your array. It's awful. So the way that we resolve this, the standard way to resolve this is you make this anonymous function inside this for loop, where you just kind of shadow the I variable. So you see we're taking I as an argument to the function, and we're just immediately calling this function, passing an I, and this works. It just kind of gives us a little closure wrapper where the I is now will keep its value throughout the asynchronous callback. So we're already starting to see where various things can go wrong when you're inventing this wheel yourself. None of it is particularly complicated, but there's just a lot of moving parts, and so that means there's a lot of places to screw up. Okay, so this is kind of what happens inside that anonymous function, right? So we increment our waiting counter. we call DB access, we give a callback. So once the database access has a result for us, it calls this callback with the data. We look for the error. If the error is there, then we have to remember that the error happened so that at the end we can do the right thing. We pass the data into the results function. We decrement the waiting counter because now this is one of our operations is finished. And then if waiting is now back to 0, we know that all of our operations are finished, and so we should move on to the next thing. And so then we check this head error variable that we've been keeping track of as all of our operations return. If it's an error, we error, and otherwise we call output with the results. Okay, Crucible 2 with ASYNC.JS. So now you can see we're pulling in the async library up top with that require. And then there's just this very pretty little thing. And this is why I really like ASYNC.JS. ASYNC.JS is, the way I think of it is, it's what you would write if you tried to take all of the common behavior from these vanilla JavaScript use cases and extract them into something that was reusable and useful. It's basically what you would come up with, only it's better. It's very well tested and it works perfectly and it's very complete. And you know what you ended up with would be kind of this buggy half implementation, right? So in this case, we can use one of async's helper functions, which is map. So like you saw in Trey's presentation, the standard JavaScript map function takes an array, operates on each item of the array, and gives you a new array with the results of operating on each item of the array. This does the same thing, only it does it with asynchronous operations. So async is smart enough to know that this DB access is going to expect a callback as its last argument, and so it wires that up behind the scenes essentially and calls DB access, accepts the callback, and then does all of the keeping track that we had to do manually, and instead just gives us a single callback when it's all finished. It'll pass us either an error or the results. Okay, looking at. Mm-hmm. It just calls so DB access accepts a callback as one of its arguments. It calls that when it's finished. That's kind of the standard callback model. Yeah, and so yes. Yeah, so async assumes that your asynchronous operations follow this model, which they generally do. This is it's kind of the standard model, and so as long as they follow that model, it just knows to stick a callback in there and that the callback will get called when it's finished. Mm-hmm. Yeah, so there are some issues if you're doing sort of the more classy type stuff. I think async will actually take care of the binding for you. I don't know if it does that all the time or only some of the time. Yeah, so there are some subtleties here. You can always also actually wrap it in another, like an anonymous function, and do the binding that you need to do. Or if you're writing CoffeeScript, then you can put the fat arrow in there and it'll take care of the binding. Yeah, I mean, I'm not going to cover all of that in this talk, but yes, there are some subtleties, and you'll have to kind of check. You know, if you're planning on doing a lot of class-based stuff, you'll probably want to try it out with classes and see if it is easy enough to do. Okay, so promises. So we start out here, and we're again calling map, but now remember this is a different map, and this API is a different API because this is the special one that we wrote that returns promises. So here this is the regular JavaScript map. Doesn't expect anything asynchronous, so it's going to iterate over IDs, and it's going to call our promise-based API DB access on each of those IDs. Remember, this is no more callbacks. This is just going to return promises. So what we end up with, our promises variable is an array of promise objects, essentially. Then we pull in this queue library. So we've hit, at this point, kind of the extent of what just promises can offer us. Promises themselves are very simple little objects. They don't really do very much. But you'll usually use them in conjunction with a library that offers some more functionality based on the promise model. So Q is a very popular one. It's a bad name, but it's a nice library. Or your given framework may offer one for you to use. They all are somewhat similar. So in this case, now that we have this array of promises, Q offers an all method where we give it this array of promises, and it will wait until all of those promises have been resolved. And then it will either call the success callback or the failure callback. So at this point, it looks pretty similar. Again, we've got our 2 callbacks instead of 1, but same thing. The success will just receive some data, and that part is finished. Or if it failed, it will receive an error message, and it will call out there. And finally, ICEDCOFFEESCRIPT. So this is a slightly, the await and defer keywords are still there, but they're in a slightly different configuration now. Now await, you can really see, is actually a block, and there's stuff going on inside that block. So inside the block, we actually iterate through the list of IDs and call DB access on each one of them. And then our defer is now taking, instead of just a variable name, it's actually taking a position in the arrays. So we'll shove the error value into the errors array and the result value into the results array. Now this example already shows us a place where ICEDCOFFEESCRIPT actually kind of makes us do a little work on our own. Because we have to kind of set up these arrays and make sure that things get into the right indexes and track the index in the for loop. And then the first time I tried to do this, I screwed it up because I ended up with, so this errors array ends up as like an array with a bunch of null values, and so I was checking if the array was empty, and it wasn't, and then I thought I had an error, and I didn't have an error. So I have to now go through the array and select only the errors that are actually errors and not nulls, and check it that way. So like it's a little more hassle, I think, than some of the other solutions. Does this more or less make sense to everyone? Particularly, I know ICEDCOFFEESCRIPT is like a little brain bending at the beginning, but hopefully being able to compare it against these other solutions, you can kind of see how it's actually pretty similar. It's just a different, dressed up in a different syntax. Yes, I know that line is, I know. I don't like that line, and I just, as I was writing this, it's like, well, I don't have a better idea, so I'll go with it. But yeah, and this is a frustration I have with ICEDCOFFEESCRIPT, is that it doesn't do quite enough for you. You hit the limits of what it does kind of quickly, I think. Okay, third crucible. This is the really bad one. I did it in vanilla JavaScript. It's really awful. I'm going to walk you through it quickly, so don't worry if you don't understand it. What I'm hoping is that you'll just see that it's painful and that you don't want to do this. So this is the whole thing. This is scrolling. No, it's not scrolling for you. All in one big chunk, and it's really awful. This is what people think of when they think of callback help, right? Now, in fairness, I yelled at you earlier about writing properly modular code, so let's do that instead and kind of extract this out a little bit. Okay, so first we write our getDBResults function. This is going to do the 2 parallel DB database accesses. We've seen most of this code before. It's pretty similar. The only difference now is that getDBResults is going to accept a callback. This is just a generic callback. And then at the end, it's going to check and see if there were errors. If there are errors, it's going to pass the errors to it. Otherwise, it's going to pass null and the database results. Next, we have getEndCollate. So this calls getDBResults. Then once it gets a result from that, it sees if there's an error. If there's not an error, it calls the collate function on it and gives it the callback so that when it's finished, it can call out of there. Now, we have networking collation. This sets up a whole bunch of stuff. So we have the counter for if our network request is pending. We have a counter for if our collate request is pending. We have the variable to store the result of the network request and a variable to store the result of the collate request. And we have an errors array to store all of those. And then we define an anonymous, well, not a function called try continue here. This is basically going to check and see if both of the network and the collate are finished, or if one of them was waiting. If they're both finished, then it's going to see if there's errors. If there's errors, we'll call back with the errors. If there's not errors, then we call back with the results of both of them. This function is not done yet. So now we start a collate request here. So we set the collate waiting variable to true. Call get and collate. In the callback there, we check for an error there. If there's an error, we push it into the error callback. Then we set collate waiting to false. We save the result that we got from that callback, and then we call that try continue. Because if collate finishes second, we need to continue at this point. If collate finishes first and network is still pending, then we have to wait. Here's our network function, same thing, set the counter, call the network thing, pass in a callback, look for errors, set the values, and again, call try continue. Does everyone understand why I have to call try continue in both these places? We're only actually going to continue in one of these, but we don't know if collate is going to finish first or if network is going to finish first. So we have to check in both places. And so I put in a little function so that I would at least only write that code once. Now that we finally have all of that set up, we can call that networking collation function. It will get this callback with final result. It will look for an error or the output as necessary. So there it is. And I tried to make this as good as I could, and it's not good. So we've pushed this vanilla JavaScript to its breaking point with this Crucible, I think. We've hit a point where it's really painful and really, really error prone to get through something like this using, implementing it yourself. And I screwed up several times in the writing of this, and this is just a toy function. This isn't even a real thing. So I would hate to do this with an actual network. Okay, let's move on to happier things. ASYNC.JS. We're going to break this up into several functions because this just is a more complicated Crucible, so it's wise to do this. So first, the getDB results. We've seen this before. Async map, iterate across the IDs, get the results from the database. That's going to happen in parallel. Now, get and collate is using a different method from the async library called waterfall. This one is going to take any number of functions. It's going to call them one at a time in order, and it's going to pass the results from the first function onto the second one, and from the second onto the third if it exists, and so on. Once it's finished doing all of those, then it calls a final callback that we provide to it. And if any one of those has an error, it will stop, and it will call the final callback with an error. So here we're giving it two functions. First is that getDB results, which fetches the two database results. Once that's finished, it goes into the second anonymous function, which takes those results and calls collate with the two results. Yeah, I've named everything callback here, which is, in retrospect, not a great choice. But basically, it passes through to those two, and then it calls this final callback that was passed into the function originally. Okay, now our third step is to put all of these pieces together and also bring in the network piece, right? So we're calling async.parallel, which is another method of the async library. This one simply takes an array of functions and we'll call them all in parallel and then invokes a callback when it's finished. So in parallel, we do our get and collate, which gets things from the database and then collates them. And we run our network function. We're using another helper from async, which I won't fully explain, but it calls a network function with an ID and will. So when both of those is finished, then this callback on the bottom here gets invoked, either with an error or with our results. So the really nice thing is that we did our error handling in one place here. Instead of having to check it every single time, we just check it once at the end. And if it fails at any point before then, async is smart enough to catch that, realize it's a failure, stop, end the steps, and bail out and call this error so that we can deal with the error. This is much, much nicer than what we were doing in vanilla JavaScript, where we had to remember to check it every single place, and every time you have a callback with an error, that's another opportunity for a developer to be lazy or just forgetful and not check the error, and then you have these silent failures, and it's just horrible. Question? Mm-hmm.
that's pretty cool about this parallel function is that you, instead of calling it as an array of functions, you call it as an object and name the object parts. When you get that result back, they'll be named results. So you have error dot, collate function, error dot, whatever you can actually name.
So it'll give you an object back instead of an array, is what you're saying?
Yeah, it'll give you an object back
Nice.
of each part.
Yeah. Yeah, so I've really only kind of scratched the surface of what async does here. And honestly, I think if the library has a flaw, it's that it does a lot, and it's sort of hard to get a handle on all of the things that it offers. But it does a really nice job of sort of thinking of all of the typical use cases that you'll have when you're dealing with asynchronous code and offering you these helpers that deal kind of succinctly with each one of them. Okay, moving on to promises. I'm going to move through these as quickly as I can without completely blowing you guys away. Okay, so again, we've seen this before. We're iterating through our IDs, and we're calling our promise-based API in that to get an array of promises. Now we are going to construct a promise that does the that takes this array of database promises. So okay, so we again call q.all on the array of promises for the database access. When that's finished, it will pass it on to this then, which takes those database results and is going to call the collate function on those results. Now all of this returns another promise. So our collate promise will be resolved once all of this has finished. So now we can kind of treat this as a discrete unit. It's just a single promise that we, once it's finished, all of the things that it contains is finished, even though really it's got like 3 steps happening in there. So then we can call q.all again with that collate promise and with just the promise for the network request here. When both of those have resolved, then it will pass it along to the then, which again just has simple callbacks for data and error. So once again, we have all of our error handling in one place, right at the end here. And part of what promises offer is the ability to handle errors in the same way and pass them up. They sort of let them bubble up through the promises. Promises are chainable. That's what we saw back here, right? So we actually chained our promises. We have the all promises, the promise of all of the array of promises, and then we chained an extra step onto it, and then we combine them all in here. So it's really nice, and I think it really handles this example pretty elegantly. And actually, so funny story, I gained some respect for promises as I was preparing this talk because of how well it handled this third crucible. I think it really is probably the most understandable of all of the solutions. And I think that's important when you're dealing with this sort of hairy stuff. Okay, ICEDCOFFEESCRIPT, final one, final crucible. Okay, so this is our first step. We're going to get things from the database and we're going to collate them. And we start to bump up against some of ICEDCOFFEESCRIPT's limitations here again. So I had to wrap this whole step in its own little asynchronous function with a callback, because that's the only way I could get it to run in parallel with the network part. Okay, so we set up our results and our errors. We have our await block, which you've seen before, go through the IDs, get the results from that. Check the errors. If there's errors, we just bail out then, right? If there's not, and it was successful, then we call that collate, and we pass it in the callback that we received at the top. So now that we've defined that function, we can set up another await block. In this one, we call the network access, and we call our get and collate. And you'll see each of those has a defer in it, and each defer takes an error variable and a value variable. So the await block knows that because there's these 2 defers in here, that's going to wait until they're both finished. So by the time it gets down to that next line, those are both guaranteed to be done. This is just the ICEDCOFFEESCRIPT magic at work here. So if there was an error in either one, we error, and otherwise we pass on the output. Okay, so that was all of our contenders, our 3 crucibles. Is there a winner? Well, I'm not going to say exactly, but I'll give you some thoughts. So you saw how vanilla JavaScript looked at the end. Like, it was hurting. We were hurting. It was not good. I really don't think that for a project of any serious complexity that you should just go without help. I think you're just putting yourself through more pain than you need to, kind of unnecessarily. So I would vote no on vanilla JavaScript, personally. Async.JS, the advantages I see in it, it's very close to the metal in that it stays very close to the callback model that most of the things you're going to be dealing with use. So it's very seamless to kind of integrate it in. It works with everything. It just uses callbacks, so it's very normal. It's simple to reason about. It stays out of the way when you don't need it, and it just shows up for the times when you know you need it. And like I said before, it's got these powerful abstractions for sort of all of the use cases that you're likely to encounter. So I like that one. Promises. The big downside is that it requires your tools to support promises and to return promise objects. And there's a special gotcha in that people can and have, this was especially prevalent in the past, it's getting better now, but it's still around, people can actually misimplement promises in a way that they don't work quite right, and then this will show up and it will bite you when you try to use their libraries with other promises and with other promise libraries, and so you'll be having this pain for someone else's mistake. And that's really frustrating. It's getting better now, but it's definitely still there, and you'll definitely, you could very easily encounter it. I encountered it after believing that it was kind of this theoretical concern. It's quite real. But usually it's very powerful and quite elegant, and provides a very nice model for conceptualizing and doing error handling and all of that. So I like promises too. Oh shoot, that's a thumbs up. Sorry, promises. Thumbs up. ICEDCOFFEESCRIPT, it's very elegant, it's very impressive. I think it's not powerful enough. It really kind of only has that one trick of it, and it starts to fall down when you do things like looping, doing a bunch of requests in parallel. It makes you do more work than I think you should have to do, and it doesn't really have any advanced abstractions. One other consideration with ICEDCOFFEESCRIPT is that, so you have to have this compile step in your build chain, and usually I don't think that's a big deal. I use COFFEESCRIPT a lot, I really like it. I think it's very easy to add a build step to your tool chain. But what you'll find when you start using ICEDCOFFEESCRIPT is that actually a lot of libraries will have like a special case hard-coded just for COFFEESCRIPT, but then they won't support other compiled languages, and so you have problems with file extensions and with getting the right compiler to run. And if you're in Node, the whole system for how it can require file COFFEESCRIPT and ICEDCOFFEESCRIPT is actually really quite janky under the hood, and they aren't changing it, and so there's weird stuff that happens there, and so it does become sort of an annoyance. In my opinion, the annoyance isn't really worth what ICEDCOFFEESCRIPT gets you. I think the other solutions offer you more and offer less frustration, and so even though ICEDCOFFEESCRIPT is really beautiful and really just like cool, I don't think it's, I wouldn't choose to use it again. Okay, that's it. Hope you enjoyed this. We'll take some questions now, but if you enjoyed listening to this, you could follow my blog where I post very, very, very infrequently on whatever developer stuff I feel like writing about. I wrote a book on COFFEESCRIPT. You could buy that. It's called COFFEESCRIPT Application Development. It is an introduction to COFFEESCRIPT and how to use COFFEESCRIPT in sort of a real-world setting. You build an application as you go, and you learn all of the pieces of COFFEESCRIPT, and you learn how to use them for an actual thing that works pretty well. You could hire me. I am a freelance developer, so if you've got some cool project that you need some help on, come talk to me or send me an email at this email address. Okay, questions? I did not. I would be interested to see that. I thought about that I should do some more research, and then I just did not have time to go and look for cool new things. But yeah, I'd be interested to see it, and I think it would be cool to see more, examples of solving these crucibles with other solutions. Honestly, I don't remember what exactly it is that they do wrong. I believe it's something about when you resolve and when you reject, and like what order that happens in, or how it happens if it's already resolved. I don't know. There's at least one bug that in particular kind of got spread around. I believe jQuery actually implemented it wrong. I mean, they didn't think it was wrong when they built it, but the way that promises evolved, it ended up being wrong, and so other things trip up on it. So there's at least one bug that a bunch of people it's like if you do the naive promise implementation, there's this one mistake that you're likely to make, and then that can bubble up through other things. I can't actually give you the exact details because I sort of erased that from my brain because it was a painful memory. But you could, there's a whole article that walks through it that a guy wrote being like, don't do this, please start implementing these right. And so if you Google, I think you could probably find that, and he will give a much better description of it.
So the underlying pattern of like incrementing when you start the functions and decrement, is that, does like async use that pattern inside of it, and the other ones, do they also use that pattern, or are they doing something else?
I think it does. I think it more or less does. I don't know if it's actually using a number or if it's keeping like an array of references or something like that. I don't know what their exact setup is, but that's more or less what you do. Like really conceptually, what you want to do is you want to keep track of anything that's out there, kind of in the ether, waiting to come back to you, so that you know what is out there. And you also know, so like, if you have things that like time out or something, then that's a whole, then your counter system falls apart, right? So you kind of have to be careful about like keeping tabs on all of your requests. So they might be doing something a little more advanced just to sort of account for all of those edge cases. You could look, the async code is really, it's pretty clean. It's like you find more or less what you expect to find there, which is nice to see. It's not overly complex. So if you're curious, you could go check it out, and it should be, it should be kind of fairly straightforward to figure out how it's doing it. Mm-hmm. Right, so that's what I had to do since my little toy API used callbacks. That's what I did in that wrapper API that I kind of briefly showed you. Was I used the queues helper to just wrap the callback up and return a promise. So yes, it's certainly not the end of the world. If you get something that doesn't, you'll just have to do a little bit more. So the other thing I should say about promises is that some ecosystems really buy in hard to promises. Like Angular, for example, is kind of all in on promises, and you're strongly encouraged to use promises when you're in that system. So if you're in an ecosystem that's really bought in like that, I'd say go ahead and use promises, because most of the libraries within that ecosystem are going to support promises. A lot of libraries do support promises, just in general, or at least have the option of promises. So part of your decision might be based on where you're working and if you expect there to be strong promises support or not. Like Node, for example, has this battle going back and forth. Some people really like promises, but not everyone does. So like with Node, it's not a shoo-in to use promises, right? Because not all libraries will. You'll have to do some work on your own wrapping stuff. But something like Angular, where they're really sort of promises is the default option, then that kind of makes your choice easier, right? Did you have anything else that you wanted to follow up on? Okay. All right. Thank you.